Hello, everyone. My name is Calin, and in the next couple of minutes, we're going to talk about 3D printing, but it's not, it's a special kind of 3D printing. I'm sure that everyone knows so far has had contact with at least one type of 3D printing machine. Today, we're going to talk about laser-based 3D printing. Here on the left side, I have a schematic representation for stereolithography. As you can see, we have a laser beam that's focused on the surface of a photoresist or substrate, depending on the application. And the basic principle is that we have linear interaction. We print the first layer, move the sample a bit, print the second layer, and then repeat this process until we have described the whole structure. I've chosen this schematic representation on the left side here because it has the most important parameters for any kind of laser processing. You see, in most laser processing, be it laser ablation, welding, striving, cutting, and all of that, you have linear interaction, and that means you focus the incident laser light at the surface of the target. And then we have linear interaction at the surface, depending on the application, and that's pretty much it. What we're going to talk about today is a different kind of laser processing, and that the target material, the photoresist in this case, is actually transparent for the wavelength of the lasers. The laser goes through it. However, if we have high enough intensities right at the focal point, we can actually force some two-photon or multi-photon absorption processes and have a different kind of interaction just in the focus spot. This actually allows us to do 3D printing at a very, very high resolution. Before we're going to talk a bit about multi-photon absorption, let's look at how exactly are we going to focus laser light. What you have here is it's not a schematic representation. This is an actual simulation for a Gaussian beam. I've chosen the Gaussian beam because it's probably the most commonly encountered intensity distribution when working with lasers, and it has a really easy way to calculate the laser spot, so the minimum laser spot, and also the depth of focus. These are two of the most important parameters because they relate with the other parameters further on. I put these formulas here because I want to show one important characteristic. I mean, it's pretty intuitive that this right here, the first formula, represents the size of the laser spots. Whenever we want to work with laser, we have to focus it and do the whole processing. It's pretty intuitive that it's going to depend on the incident wavelength. However, what's really important is that it's directly proportional with the focal length of the optics that we're using and inversely proportional with the diameter of the incident laser spot. So what it means here, what this formula shows us, is that the shorter the focal length, the smaller the laser spot in the focus, and the larger the diameter of the incident beam, the smaller laser spot in the focal, at the focal distance as well. Another important characteristic is this one, the second formula. This is called depth of focus. You could see in the simulation here, you have this green yellowish color over here. This pretty much tells us the volume in which the laser intensity is high enough for our processing. And what the important part is that when we have a longer focal distance, as you see here, it depends with the square of the focal distance. So the longer we have the focal distance, the higher the depth of focus will be. However, the laser spot will be bigger as well. What it tells us is that if we have a high enough depth of focus, that means the laser processing is not going to be sensitive to the flatness of the target. However, if we, for example, if we are going to use a microscope objective with 100 times magnification, if the flatness of the target actually changes with, let's say, 2 micron, it's going to go out of focus. This is very important when we're trying to do high resolution laser processing. Okay, now let's look a little closer to the multi-photon absorption processing. There is a trick here. If we are actually using 2-photon or maybe 3-photon absorption processes to do 3D printing, we can actually process materials very much below the diffraction limit. So the formula from the slide before shows us exactly how small the business spot is that we can obtain with a specific set of optics. However, using this kind of a setup, we can actually go much lower than what's theoretically possible for the central wavelength. And the trick is that of course, we have to use a Gaussian beam, and this is primarily the reason I've shown the Gaussian intensity distribution, is because we have to use a Gaussian beam, and we know that for a specific photoresist, there is a certain energy density above which, if we call it a threshold level, above which 2-photon absorption becomes predominant. And when the trick is that we use a Gaussian intensity distribution to actually just cut the tip of the Gaussian beam to have the 2-photon absorption processes, and that means we can process materials way below the diffraction limit. Now, this schematic, maybe it's not really describing the whole phenomenon really well, so I've chosen to show you an actual picture of what's happening. Maybe this makes everything more clear. So on the left side, we have linear interaction, the most commonly encountered laser processing method. We have an UV laser in an acrylic material, and we can see the fluorescence, and we can see that the laser strongly interacts with the material over the whole volume that it propagates through. However, in the second case, we have an infrared laser, and when we shoot it, we make it propagate through the material itself. We can see that the material is transparent, so the fundamental wavelength does not interact with the material, or maybe it does interact because it propagates through it, but the interaction is very weak because of the low absorption. However, you can see here, maybe you can see the small spot over here, but you have a zoom in on the cutout over here. You can see that we have the same kind of fluorescence, the same kind of fluorescence we have on the left side. What happens is that we have 2-photon absorption, and it's like we are having the second harmonic of the incident laser beam interacting with the material, but the point is it's only in a very small volume. And we're using this trick to actually initiate a polymerization process somewhere inside the photoresist and just move it around in a 3-dimensional pattern to describe the the structure, the 3-dimensional microstructure that we want to fabricate. And the point, another advantage in this case is that we can actually freeform any kind of structure. We do not have to, you're not obligated to use the layer by layer fabrication. You can go just straight up and it's going to work. Okay, before moving on to the material to explain what exactly happens inside the photoresist, let's talk a little about general high-resolution processing, especially for 2-photon absorption, because we have some parameters that are very advantageous. They're not necessary, but they're very advantageous. For example, for the laser source, we have the pulse width. Shorter is often better because shorter pulses allow us to obtain even smaller volumes. We call it voxels. It's a volume pixel. So the volume the prolate volume in which we have multi-photon absorption, but not always, because shorter pulses, for example, from an economical point of view, the shorter the pulse, the more expensive the equipment. And this is actually very important. It's one thing to have a femtosecond laser, and it's another thing to have a picosecond laser when it comes to how much it costs, maintenance and acquisition. The intensity profile, the transverse intensity profile, has to be a Gaussian intensity distribution, at least in this case. Maybe you could obtain it with a top-hat distribution as well, but it's going to be a bit more difficult, and the shape of the whole volume is going to be less advantageous, let's say. Now, the repetition rate is advantageous only if we are interested in doing faster laser processing. So if we have a high repetition rate, then we can move the laser beam faster inside the photoresist, and then that means we can do the 3D printing a bit faster. Now, the beam delivery has to be tight focused. I mean, it doesn't have to be tight focused, but it really helps to be tightly focused. For example, if we want to obtain larger structure than we usually do, we can use lower magnification or maybe just a lens. However, the less focused the light is, the higher the energies that we have to use because we have to compensate to obtain the energy density. And this might not always be possible because it's not a linear progression from the surface, the laser spot and the energy that we need. It's not linear. Now for laser processing in general, if we want high resolution and high accuracy samples, we have to keep the laser light stable. We have to keep it from moving, and then we move the sample around. The disadvantage is that it's going to be a bit slower, but we're going to obtain much higher resolution microstructure. And if we are not interested in a very high resolution structure, we can just use, for example, a galvo scanner and move the laser very fast and still obtain satisfying quality of the microstructure. Now, for the material interaction, I've already mentioned the part about linear absorption or multiphoton interaction. For the multiphoton interaction, I always mention multiphoton because we can actually do it with 3 photons and maybe 4 photons. It doesn't have to be 2 photons. 2 photons is more, let's say, approachable. It's easier to obtain. Okay, now let's go a bit, let's talk a bit about the material itself. So the main difference between stereolithography and three-dimensional lithography is the existence of this so-called volume pixel or voxel. This is the main difference. So in the stereolithography case, we have linear interaction. So whatever the laser is propagating through is going to interact with it. So for example, if we want to do polymerization, if you shoot the laser, it's going to start a polymerization process right at the point of contact, be it the focal point or not. However, in the three-dimensional lithography, it's going to happen only at the focal point. No interaction is going to happen anywhere in the volume of the photoresist, even if we have laser light. Now, the photoresist itself for two-photon polymerization has to be transparent to the fundamental, the central wavelength of the laser, because it has to be to propagate through the photoresist without changing the temperature or any parameters of the photoresist. And of course, we have to have a high absorption to the second harmonic to initiate the polymerization process. I'm going to talk a bit about this in the next slide. Now, most often we have chain reaction polymerization involved with two-photon polymerization, but you can actually do it with cross-linking as well, if needed. The point is that even if we can use photoresists that are based on cross-linking, we kind of lose all the advantages that two-photon absorption offer us for laser direct writing. But for chain reaction polymerization, we do not need to put the sample through spin coating. We do not need to bake it. We do not need to post-bake it. We don't have to do anything. We just put a drop of photoresist and just focus the laser inside it and start having fun. Okay, first I'm going to show the thing about the sample preparation, let's call it. I'm going to show it a bit later, but first let's talk about what happens inside the photoresist itself. So most photoresists that are specialized for this kind of laser processing are liquid, and they have 3 main components. The monomer, of course, because we have polymeric structures. The photoinitiator, because this is the most important substance inside the photoresist for this kind of processing. And of course, some other substances to control the viscosity, the refractive index, and so on. So the main idea is that when we shoot the laser inside the photoresist, we have two-photon absorption only at the photoinitiator. Nothing else interacts with the laser beam. So we ionize the photoinitiator molecules and they become reactive. When they become reactive, they start chaining together monomer molecules until they encounter another photoinitiator molecule to close the chain itself. So what happens, we pretty much ionize photoinitiator molecules, and a lot of random polymeric polymeric chains are starting to form inside that volume, and they kind of stick together because they're random. And that's the whole point. That's why we don't need any kind of supplementary or pre-baking, post-baking, and all the other processing parts. At the end, we just wash the structure to dissolve and wash away the remaining unirradiated photoresist, and we obtain our desired three-dimensional structure. Okay, so this is pretty much the whole pre-processing that we have to do. It's very different if you have used UV lithography, for example. You know all the processes that you have to do beforehand. You have the photoresist. You have to have a good surface quality. It has to stick. It doesn't have to be hydrophobic. It has to be hydrophilic, and you put it through spin coating and baking and all of that. In this case, in two-photon polymerization, you don't do anything like that. You just put a little drop of photoresist. It's a viscous yellowish color photoresist, and that's pretty much it. You just start shooting the laser at it and start actually printing the microstructure. So it's that simple. And at the end, we just remove the substrate. In this case, it's a transparent substrate. At the end, we remove the substrate, immerse it in a specific solvent, leave it there for 3 minutes, 10 minutes, 15 minutes, depending on the photoresist, and that's pretty much it. Now, this is a schematic representation on exactly what's happening. So we have the a glass substrate in this case. We can use also opaque substrate, but we have to put the drop on the other side. So we put the drop, the photoresist drop on the substrate. We focus the laser right at the surface between the glass and the photoresist, because our structure has to stick to something, has to stick to something. And we have here different different setups. For higher resolution, we have immersion oil, and for opaque substrate on the last image. Now this is the installation that we are using. It's simply a femtosecond laser. We have the parameters on top. It's an erbium doped fiber laser. We have a very high repetition rate and an inverted microscope. We can change the objective and to obtain different kind of laser spots. Now I've talked a bit about what it is, how we obtain the structures, but still it might not be so clear what exactly can we do with this kind of technology. So I'm going to show you this picture. So this is a castle. This is one of the most famous castle of Vlad Tepes, so Dracula. And this was done with two-photon polymerization. Now, this is an electron microscope image. There's something missing from this image. Can anyone? The scale, exactly. The first thing you do is put the scale on the image when you have microscopy image. And this is the scale. On the right side, you have the same kind of castle, but on the right side, you can see there the scale is 300 microns, and on top you have a human hair, so that you can imagine the size of the castle and the human hair on the left part. Okay, so this is pretty much what we can do. And on the right side, we can see that we have the windows and the stairs and all the details. You see the windows here and everything, every little tower. So this is pretty much what we can do with the technology itself. And we could actually print it on the human hair, but it was quite difficult to align, so I just left it near it. Okay, so I've said that we can go below the diffraction limit, but how low can we go? Well, from our previous experiments, the lowest I could obtain was 90 nanometers. And for a incident wavelength of 700, almost 800 nanometers, I think it's quite below the diffraction limit. It's low enough to call it below the diffraction limit. However, there is a trick. I focused a bit into the substrate to actually obtain 90 nanometers. If we go somewhere three-dimensional structures, all I could obtain was about 200 microns tops. This was the highest resolution. And 200 nanometers tops, yes. Okay, so what can we use it for? Let's talk applications. Well, this over here, we have diffractive optics. So this is a hologram, 8 levels, 2 by 2, well, 2 and 2.4 by 2.44 millimeters. So it can do with using this technology, we can actually build microstructures, complex microstructures on larger areas. So relatively speaking, larger because it's still 2 by 2 millimeters. However, the fabrication time is a bit higher, of course, because we have to scan everything. We can use it to do microstructures that are used to force a stronger laser beam focusing. These are some cone-shaped microstructure used for, so intended for laser-driven particle acceleration. Okay, so the femtosecond laser comes somewhere around the top area of the structure itself, and then it's going to be reflected off the walls because it's going to be, we're going to have ablation. It's going to act like a metal surface, a metal-like surface, and it's going to reflect the electromagnetic field and focus it right here on the top. So this target has 100 microns. Oh, we have the parameters on site here. So the height is 100 microns, and the top diameter is 100 microns as well, and the bottom one is 10 micrometers. So you can see the kind of, this one has parabolic shape wall. That's why it looks like it's intended. It's on purpose. Of course, tissue engineering, a lot of tissue engineering and biomimetics and high, topological surfaces, super hydrophobic structures, and all of that. These are all three-dimensional structures. We use it mostly for osteoblast-like cells, or for bone tissue engineering. Photonics, we have photonic crystals, and here we cannot obtain very small laser spot size, but the important thing is that we have a very, very high positioning accuracy. This is important for small photonics. And on the right side, we have integrated optics or photonic circuits. We have a Bragg diffraction grating, some waveguides, an interferometer on the side over here. And if you've been present to to yesterday's presentation, I've talked a bit about the microstructuring that we can do on top of the PMP materials. But I didn't get a chance to actually pinpoint the direction we're going into. So these are only the beginning tests to find out the parameters that we need to do all the processing on the surface of the PMP material. But the ultimate objective, if we can get there, is building this kind of photonic structures. Okay, so we have diffraction gratings and waveguides and things like this to actually control the amount of light that goes into the PMP material, that goes out of the PMP materials, and similar things. We can actually build micro-optics and photonics using this technology. And that's time. I think I've actually did it all right.